Thank you, Francesco, and thank you all. Let me first thank His Excellency the Duke of Mantua for inviting me to this lovely workshop again. And even more because when he first wrote to me asking, inviting me to the meeting, he asked me, what would you like to talk about? And I said out of the box just for lack of a better choice, because back then I had no idea. But I did anticipate somehow, and that's one of the advantages of getting old, that the workshop would be flooded with trials. And if not trials, big data. And if not big data, real-world studies, and so on and so forth. So I thought to myself, if I even vaguely mention a trial or a real-world study to you, I would, at this point, being last in the meeting, bore you to tears and bore myself to tears. So what I thought I might do is to do a little courtesy to the audience, which is predominantly young people, and to give you, rather than a full novel, 3 short stories with the idea of pricking your brains. So, my limited conflict of interest, unfortunately. So I'm going to develop reflections on metabolomics and metabolism, metabolomics and coronary artery disease, and then type 1 diabetes. So let's start with metabolomics and metabolism. Of course, omics, metabolomics, proteomics, transcriptomics, etc., are a big deal these days. But I want to go over my personal journey through metabolomics. This is the mother of 2 unlike daughters. So you have a compound which is butyrate, and the addition of just 1 hydroxyl group gives you either beta or 3-hydroxybutyrate or alpha or 2-hydroxybutyrate. And this is just an epimeric difference. And mind you, the raw formula and the molar mass of these 2 daughters is identical. However, if metabolism is not done and over with, beta-hydroxy or 3-hydroxybutyrate is a ketone body. And ketone bodies are principally made in the liver, but also in the kidney to an extent that we've not been able to measure in humans. But in the liver, we know that if you feed fatty acids in excess of what can be stored, these fatty acids will be beta-oxidized to produce a lot of acetyl-CoA, and this, if the supply of fatty acids is excessive, will induce ketogenesis. And so through acetoacetate and then the reduction of that to beta-hydroxybutyrate, you produce the main circulating ketone body, which is beta-hydroxybutyrate. It's important to remember that the first step in the condensation of acetyl-CoA to acetoacetate is a very familiar enzyme. It's hydroxymethylgluteryl-CoA, which is also a committed step in the synthesis of cholesterol, but with the important difference that this one is the mitochondrial isoform, whereas for cholesterol, it is the cytosolic isoform. And then the second thing which you may remember from recent biochemistry, particularly the younger ones, is that the human liver can make ketones, but doesn't have the enzyme to use ketones. So the entire production of ketone bodies is exported into the general circulation. So if there is an excess of fatty acids in the context of an insulin to glucagon ratio, which is still one of the main regulators of hepatic metabolism at large, not just ketogenesis, as is the case if you treat someone with an SGLT2 inhibitor, There will be a stimulation of ketogenesis and an increase in the production of ketone bodies by the liver. Again, we don't know anything about the kidney. So once again, the excess acetyl-CoA can also be disposed through the cytosolic form of the enzyme to actually make mevalonate, which is the first step in the synthesis of cholesterol. And this may explain why in the studies, in the phase 3 studies and the trials of the SGLT2 inhibitors, it has been invariably found that the circulating levels of LDL cholesterol are actually slightly increased. And this was initially thought to be a bad signal for cardiovascular disease, but this idea has now been obviously dismissed. So then, one target of this supply of beta-hydroxybutyrate is the myocardial. This is a myocardial cell which can utilize not indifferently glucose or fatty acids to produce energy in the mitochondria, which is the power plant, with one important difference, that the utilization of glucose is gated because you need insulin to bring glucose into the cell. And then there is also, in patients with type 2 diabetes, a decreased activity of pyruvate dehydrogenase, which is the first step into the TCA cycle. Whereas the free fatty acid will flux into the cell, any cell, including the myocardial side, according to a concentration gradient. So in patients with diabetes, regardless of treatment, there is already a preference for the utilization of fatty acids versus carbohydrate versus glucose for the purpose of producing energy and therefore contraction. We should not forget that this is not the case of a normal heart. This is the diabetic heart, and it's been demonstrated over and again. So one possibility is that by providing an excess of beta-hydroxybutyrate, you may be changing the substrate mix that is offered to the myocardial side and doing it a favor, because energetically it's more efficient to use beta-hydroxybutyrate and in the order glucose, and last is free fatty acids, use of oxygen for production of energy and contraction. Now, have we demonstrated this possibility in humans? Well, this is a study that I would have loved to do myself if the ethics committee had approved, which they didn't, the protocol, but it was done in Denmark. What they did in people, they infused beta-hydroxybutyrate, and of course it was an acute experiment, and the ketone levels were brought up into the millimolar range, so it was not exactly physiological. But what they saw was, first of all, the myocardial blood flow was increased upon infusing ketones, both as a whole and in the left anterior, the circumflex, and the right coronary artery. So this goes back to what we heard from Angelo this morning, that one main function of the heart is to increase perfusion in response to an increased demand, and that's called coronary reserve. And apparently, in this experiment, ketones are enhancing the ability of the heart, these are normal subjects, to tap the coronary reserve. But this study was also done with the use of fluorodeoxyglucose and PET scanning. Now, fluorodeoxyglucose is an analog of glucose. You can scan the the fluorinated FDG, and what you see on top is the distribution of the glucose analog, and therefore of glucose, in a midsection of the heart of a normal subject. So you see the uniform uptake, that the red code stands for very intense uptake of glucose. Upon infusing beta-hydroxybutyrate, there is a diffuse reduction of the signal, which means that you do end up with a substrate substitution, shifting from glucose onto the beta-hydroxybutyrate, which means that by its own nature, the heart likes ketones. Now, does that translate into a clinical benefit in the context of SGLT2 inhibitors? Nobody knows. It's difficult to tell for two reasons. First of all, you would have to do one of these complicated and sophisticated studies. But second, the rise in ketones that is seen normally in patients with type 2 diabetes on an SGLT2 inhibitor is way smaller than the rise that was applied acutely here. But it's chronic, so the question is just open. And I don't know that it will ever be possible to gauge what effect this slight hyperketonemia due to the treatment can possibly have on the heart. There is another study, the slide of which I lost somehow, where they've done the same thing. It's actually the same group. But they did the infusion of ketones in patients with heart failure. And what they found was that not only was there an increase in perfusion of the heart, but using echo and MRI, they also demonstrated an increase in ejection fraction, cardiac output and ejection fraction, and a reduction in peripheral insulin resistance. So once again, the proof of concept, I think, is there. To translate that to a clinical benefit, it remains to be seen if you have a good ethics committee, which we don't. But these ketones not only go to the heart, they go everywhere, because the transporter to import ketones from the circulation into cells is widespread. It's expressed virtually in all tissues. And there are two areas where this might be of further interest. One is the kidney, and the other one is the brain. And I should mention that at this wonderful workshop, there has been very little mention of hypoglycemia, as you know, but also the brain has been kind of left alone, except for the talk of our colleague, the neurologist from Holland. But I think it will be next in the workshop 3 years from now. And that is because it's long been known that ketone bodies are an important source of energy for the brain when glucose is lacking. The brain cannot use, neurons cannot use free fatty acids, unlike the myocardium, but they are very avidly utilizing ketone bodies. But leaving the brain apart for the next meeting 3 years from now, what about the kidney? So recently, in collaboration with the group in Turku, who have wonderful PET facilities, Eleni Rebelos has done one of the few studies of kidney metabolism that you can find in the literature. Because if you ask again the question, what does the kidney do metabolically? The kidney has a very tough job. It has to reabsorb all sorts of molecules and electrolytes. If you just calculate the ATP equivalent of reabsorbing approximately 200 grams of glucose a day, which is the amount that is normally filtered through the glomeruli, you realize that the reason why the kidney takes up about 20% of cardiac output and works all the time, not episodically like skeletal muscle, that means that metabolism, the availability of substrates and the substrate mix is very important for the kidney. But if you go back to the literature, as I tried, and look at what is known about kidney metabolism, you find rats and mice everywhere and humans nowhere. So this is an area where those of you who have ideas can develop into. For example, it's now possible with these beautiful imaging techniques that we have to visualize the kidneys in a subject, a type 2 patient like this, and then calculate the size of the kidneys, right and left. Then you can also use oxygen to measure, or acetate, to measure perfusion of the kidneys. And you know that there is a difference between the cortex and the medulla. and you can calculate the differential perfusion of these two areas of the kidney and relate that to metabolism. And then in this study, another tracer, FDHA, which is an analog of fatty acids, labeled again with fluorine 18, was used to calculate the cortical and medullary uptake of fatty acids by the kidneys. And this is the first study of the kind that I'm aware of. And so then you can start looking at quantitative measures, for example, finding, perhaps not surprising, that the uptake of free fatty acids by the human kidney is related to the whole body oxidation rate. So when you have an excess of fatty acids, there will be an excess of fatty acid oxidation, as I mentioned previously, and this will be reflected kind of in a parallel way in several organs, and one of them is, in fact, the kidney. And this is true of the cortex as well as the medulla. And if you then again go to rats and mice or in vitro models, you find that this daughter of butyric acid, beta-hydroxybutyrate, has been claimed to have a range of metabolic actions. The most important ones to me seem to be coronary vasodilation, which must be an effect on the small vasculature, not the subepicardial vasculature, but the smaller vessel, scavenging of ROS, stimulation of insulin release. This has been known forever, that if you take an isolated pancreas or islets and you perfuse them with just a little bit of beta-hydroxybutyrate, you enhance the glucose response, the insulin response to glucose. But also reduction of sympathetic outflow, and this again has been mentioned yesterday as one of the potential mechanisms to explain why, when you give an SGLT2 inhibitor, there is a drop in blood pressure, but no compensatory rise in heart rate, which obviously suggests that you've toned down the response of the baroreceptors in the big vessels. Now, what about the other daughter, the alpha-hydroxybutyrate? How did I stumble upon this? This was a fishing expedition. This was metabolomics done on a bunch of people. There were 400 people which were clamped, so the M value was calculated. And we took the extremes of the M value. So these were non-diabetic subjects, so the very insulin-resistant and the very insulin-sensitive subjects. And we did metabolomic screening to see which metabolites, which cluster of metabolites would be best associated with the presence of insulin sensitivity or insulin resistance. And when I looked at this output from Metabolon, which is the company that did this, the first guy was alpha-hydroxybutyrate. And to tell you the sincere truth, I thought to myself, oh, it's a ketone body. But it's the alpha, not the beta. And this plots on a completely different area of the big metabolism chart. We also looked at whether this was something, in a way, very statistically significant, but chancely, sort of biologically. So we looked at patients undergoing bariatric surgery, clamped before and after surgery, who lost some 40 kilos a year after surgery. And you see on the clamp, insulin sensitivity was much improved, as expected, and the level of alpha-hydroxybutyrate, which was increased in association with insulin resistance, was actually in parallel reduced. So not only is there a marker, but this is a flexible marker. So where is this thing? It's here. Don't panic. Alpha-hydroxybutyrate is in NADH, NAD exchange with alpha-ketobutyrate, and this is a metabolite of amino acid metabolism. And the thing is that we've known for a long time that oxidative stress consumes glutathione. And the glutamate, cysteine, and glycine that are components of glutathione are essential to be reconstituted in order to return the glutathione level and its antioxidant activity to normal. So what happens is that in the presence, this was a model, of course, a metabolic model, in the presence of oxidative stress, there is a consumption of glutathione, there is a reduction of glycine, which has been associated with insulin resistance, and there is an increased transfer by transsulfuration of methionine through cystathionine to cysteine to reconstitute. But the byproduct of this is alpha-ketobutyrate, which then converts to alpha-hydroxybutyrate, and that's what we measure. In addition to that, there is also the concept, which is increasingly well supported by physiology and biology, of substrate overload. We know that particularly in the insulin-resistant and obese person, there is an increased concentration of branched-chain amino acids, free fatty acids, which overload the capacity of the mitochondrion of the TCA cycle to oxidize these substrates. And as a consequence, there is an escape of propionyl-CoA, which is the mother of alpha-ketobutyrate and therefore of hydroxybutyrate. So we concluded with a model whereby the increased concentrations of this person, of this molecule, stands for an increased degree of oxidative stress in vivo, as well as a marker for metabolic overload. And the metabolic overload is now being applied not just to peripheral tissues, but to beta cells as well. And then the final proof of concept was to look at whether in the risk study and in the Botnia study, which Leif very kindly gave us the data to look at, there was any predictivity of high hydroxybutyrate levels for the subsequent development, so for the incident dysglycemia or diabetes. And much to my surprise, as you can see, independently of gender, familial history of type 2, age, BMI, and even fasting glucose, which are the typical predictors of incident dysglycemia or diabetes, there was an independent predictivity of these levels of alpha-hydroxybutyrate for incident dysglycemia in both the risk study, which were healthy Europeans, and in the Botnia, which was a population based with an enrichment in family history of diabetes. So now we have a model to explain why this molecule is increased, and this has now been confirmed in other studies. And in the studies where you don't find it, is because you didn't look for it. Now, metabolomics and CAD, this is all unpublished stuff that I put together just for this meeting, actually, and it's to do with coronary artery disease and metabolomics. What do we know about predictors of severity, extent of coronary artery, atherosclerotic coronary artery disease in people? And here I have to tell you that we did collaborate in a study where there was this integrated network analysis that puts together metabolomics, transcriptomics, and enzymes, and based on tissue measurements. And when this was done, another strange guy came up at the top of the list of the metabolites associated with insulin resistance. And this was mannose. Now, I bet that, like myself, very few of you would remember what mannose is. Mannose is an epimer, a C2 epimer of glucose. It circulates at very low levels, about 100 times less than glucose. And as you can see, it's taken up through transporters into cells, where it is phosphorylated by an enzyme that looks like hexokinase 1 and 2. And then the mannose and the fructose 6-phosphate So the two first steps, the phosphorylation in the metabolism of glucose and mannose, can exchange. So if you have an excess of one, that will drag the other, and vice versa. And this was not terribly interesting until we measured directly, and this is IMPRESS, the concentration. We had to set up a method which is quite difficult because of the low concentrations. We looked at what this was like, what this mannose levels in the blood look like in control subjects given either a saline infusion or a euglycemic insulin clamp, the standard one. And we also looked at the same in a group of type 2 patients. This looks very much like what you would see with free fatty acids, with branched-chain amino acids, and even with glucose. So there is, in controls, the insulin reduces the levels. This is impaired in the patients with type 2, and it's obviously unchanged in the control study with saline. And we even found this correlation between insulin-induced drop in mannose concentrations and insulin-mediated glucose disposal, confirming that this is a biomarker of insulin resistance. But then it occurred to me that one thing the mannose does is to link up with guanosine diphosphate and enter the glycan and glycan metabolism. And glycan metabolism is early atherosclerosis. So then there was this epidemiological study carried out by Nick Wareham, where using screening metabolomics, they looked at mannose and found that this was an independent predictor of cardiovascular events. And it was actually one of the strongest ones because it resisted adjustment with confounders. So this is the study that was done and published a couple of years ago. And as you can see, whether you use this or the other confounder, presence of diabetes or not, the association of mannose with incident cardiovascular disease now as a syndrome is always on the right side of the unity line. And this was statistically significant. This was a very large, this was the British segment of the Norfolk study. So I took advantage of a study that we are doing where we have patients for different purposes undergoing a CCTA, which is a coronary scan, a 6-4 slice tomographic angiography. And I wondered, this is clinical evidence, do we have any association of this thing with the actual involvement of the coronaries? And these are slides, very preliminary, that I put together just before coming here. So I divided the population, which was about 500 people, all undergoing CCTA, and divided into those with completely clean coronaries and those with CAD, coronary artery disease. And as you can see, the mannose levels follow, as well as, the cardiologists, they can measure total plaque volume, and even using these sophisticated scans, they can even give you an idea of the plaque composition. And this again resonates with what Angelo was talking about. And what we find is that there is some association with total plaque volume and with these indices of involvement of the coronary tree that is explored by CAT. So the segment stenosis score, the segment involvement score, which is the quality of the plaque, and so on and so forth. Now, this is very preliminary, needs to be cleaned up and confirmed, but at least it suggests that this is a biomarker, circulating, measurable, quantifiable biomarker of not only clinical cardiovascular events, but even the presence, the extent, and the quality of the plaques, the atherosclerosis in the heart. And because I'm already late, I get on to the final point, which is completely different. It is type 1 diabetes. And type 1 diabetes has become almost an orphan disease. You know, we have 13 classes of drugs for type 2 and just insulin and little else, actually, for type 1 diabetes. And it occurred to me that I had in my memory, that in patients with type 1 diabetes, documented type 1 diabetes, meaning that they are positive on autoantibodies and are on insulin, insulin treatment, etc., there may be some residual endogenous insulin production. And of course, the interest for our colleagues in pediatric endocrinology and also adult diabetology is whether these residual beta cells can be brought back into some action to delay, reduce the insulin need or delay the progression of type 1 diabetes. So the question that I asked was, how much really residual endogenous secretion is there in type 1 diabetes? And through collaborations, and this is the general theme of my presentation, this is all done through collaborations, I've put together data in 77 patients, adult patients, with relatively short duration of diabetes, with a normal BMI, these are young people, and with a relatively well-controlled type 1 diabetes, and a control group that I could extract from previous data of non-diabetic subjects matched on age and BMI. And so the good thing about this was that each of these subjects received a mixed meal test. And on the test, the C-peptide was measured. And using glucose and C-peptide, we could reconstruct insulin secretion rates and calculate how much insulin these two groups were putting out. Mind you, the fasting C-peptide averages, actually, that's the mean, 0.3 nanomolar, which is the threshold that's clinically used to say there is no residual insulin release, and this person is indeed bona fide a type 1 diabetic. There is a spread. But in any event, the fasting C-peptide, which is what currently is used, was significantly less than in normal people, as you would expect. And this is the average insulin dose expressed in units per kilogram per day that these subjects were on. So, what did we find? First of all, we looked at beta cell glucose sensitivity, so beta cell function. And without much surprise, we find that it's drastically reduced in the patients as compared to the controls. We also had an estimate of insulin sensitivity. It wasn't a clamp, it was one of those proxies, but we also found a significant 30-25% reduction in insulin sensitivity. And these were lean, young people with well-controlled diabetes. So the idea that type 1 diabetes is a model of insulin sensitivity as opposed to type 2 diabetes is kind of uncertain. And here you see the dose-response curves for insulin secretion in response to plasma glucose excursions during the mixed meal. And obviously, as you would expect, the curve is shifted down and to the right in the type 1s as compared to the controls, giving just a visual picture of the defect in beta cell glucose sensitivity, which is the ability of the beta cell to sense a change in glucose levels and to respond to that level. However, when we calculated the total amount expressed in the same units of insulin endogenous that was released by these people over a period of 24 hours, and there are some approximations here, we had to make some assumptions, and compared that with the control group, we came up with a number that is incredibly similar. So, in fact, not only is there residual insulin production, but this is large residual endogenous production. And that goes on top of the exogenous insulin. So overall, these people are exposed to much more insulin because they are insulin resistant. But the components are about half the exogenous insulin treatment, and the 0.5 is the endogenous insulin release. And what are the correlates of this? Well, you see here that this endogenous insulin release correlates inversely with exogenous insulin. So the people who have a larger endogenous reserve of insulin are also the ones that require less exogenous insulin, which is, not unexpected. What was less expected is that glucose sensitivity, as measured from the mixed meal test, was very well reciprocally related to the insulin dose. So not only is there production, but the sensitivity of the beta cell, which is the main function of the beta cell in physiological terms, was related to the exogenous insulin dose. So the better the patient's insulin beta cell glucose sensitivity, the lower the need for exogenous insulin. Now, I want to leave this idea with you because it came as a surprise to me, so maybe it will surprise some of you at least, to kind of do away with the concept that at diagnosis of type 1 diabetes, the game is over because there are no beta cells left, and all that is left for us to do is to use exogenous insulin. Now, the extent of the defect can be different from person to person, and depending on factors that are measurable. And so I got a project going looking at patients collected in the context of TrialNet, which is this large collection of either patients with type 1 diabetes or first-degree relatives of patients with type 1 diabetes, followed up with multiple mixed meal tests over time, and looking at the efficacy of different interventions that you've all seen published in the New England Journal of Medicine, for example, mycophenol, rituximab, oral insulin, intravenous insulin, and so on and so forth. So the idea is to pool the placebo arms of all these trials to get some idea of the natural history of this endogenous insulin release. Is it related to the duration of diabetes, time after diagnosis? Is it related to the time of onset of the diabetes, children versus adults? Is it related to the degree of glycemic control? What is it due to? And then, against this background, what is the effect of the various interventions that have been tried and published recently? So, to conclude, I think I've given you, rather than a full novel, 3 short stories as food for thought for those of you who can still get excited about a research project like myself. Thank you.
Thank you, Ellen, so much. Very interesting, very exciting. Questions? Leif. And Riccardo, too.
Don't ask me about clusters. I'm not going to answer.
No, Ellen, great talk. I promise not to ask you about clusters, but I really like your last about type 1 diabetes. Of course, I would like to ask you about genes. You should really relay the residual insulin secretion to genes, some HLA and some others. But my key question, did you measure proinsulin? Did you measure proinsulin?
Yes, and it kind of follows beta cell glucose sensitivity. So it's better preserved and correlates with beta cell glucose sensitivity. There was an intervention to this that I did not show you because it's confidential data. These were all subjects with multiple autoantibodies positive. And the age you have seen, the BMI you've seen, and there was also family history of mixed diabetes, as you've shown years ago. Yeah.
Riccardo and Stefano later on.
Well, a wonderful lecture, as usual. I have 2 short questions. First, what is in your mind the place of mannose as a biomarker? because you have shown a very beautiful correlation with insulin sensitivity. And then when you go on and show how it can be a biomarker, coronary disease, etc., etc., in your mind, this is a sort of another biomarker of insulin sensitivity. So if you had a good biomarker of insulin sensitivity, Manos would not be so significant, or it's a new additional story by itself? And
Right.
this is my question.
It's the latter, because I'm not so interested in the ability to improve predictability. This was also done in the epidemiological study, and it's there. It does not improve the area under the ROC curve in a big way, but nothing does, actually, if you put in the obvious confounders. But I'm not so interested in, that's just the first step. Does it correlate or not? Is the correlation independent of confounders? And it is. To me, the interest is in what is this doing? And it opened up the possibility of looking at the N-glycan pathway, because mannose is both incorporated into N-glycans as well as released when the N-glycans are broken down. So, and the N-glycans is the matrix of the vascular wall. So it's been in many biology studies directly related to the state of the vascular wall and atherosclerosis and so on and so forth. Second question?
The second question relates to the individuals with type 1 diabetes. I've noticed that their insulin dose extrapolated to the whole day is about 12-14 units per day. These are the typical patients that we see, and we define clinically in honeymoon. So to some degree, the great interest of your study is that you offer, first time to my knowledge, a nice, solid pathophysiological basis to our assumption as body physicians that we still had quite good beta cell functional mass working, and we are just replacing only a fraction of something which beta cells were doing. I think that the most interesting part is the one you're alluding to at the end, that you are going to see what a series of intervention can do with this beta cell functional mass. I'm wondering whether you share my view.
I do.
Ellen here. Great. Just a question about, you showed that the glucose sensitivity is correlated with the insulin requirement. Is there anything else that is correlated with the glucose sensitivity? In other words, is there any factor independent of the condition that really affects the function of the beta cell? And because of that, you have this. So you have a very narrow population, but yet was that an effect on the spread of the BMI or whatever, or other factors and so on and so forth?
Yeah. Excellent question. It's true that I'm married to the beta cell glucose sensitivity, but I hope that, this is a small sample of subjects. The idea about this pooling project, which we have actually funded, not very generously, but funded by the NIH, is to have a much larger, in the hundreds, pool of patients with type 1 diabetes who've all had a mixed meal. Not only that, but there is data for repeat over time mixed meals. So not only this should allow us make it possible to look at other factors, age, BMI, glycemic control, exogenous insulin dose, etc., but also look at the time course. Those that get worse and those that get better, what are the predictors in this population, as well as looking at interventions. So we are going to be pulling together all these trials. There are, I think, 9 trials that have been published and 1 that is ongoing, using different approaches. Again, as I mentioned, oral insulin, intravenous insulin, rituximab, imatinib, mecofenol, modulating the immune response or this or that, and we are going to be looking at these effects in this way.
And the curiosity, you mentioned, 2 potential biomarkers, one for diabetes development and one for CAD. Is there any biomarker that is sort of associated with the 2 conditions that would bring them together?
What you need to do to answer that question is to measure both in the same big cohort. And this has not been done yet, because for these measurements, for either measurement, we had to set up a liquid chromatography gas mass spectrometry technique, because these are the alpha-hydroxybutyrate falls into a very crowded area of other metabolites where you have to purify, and the mannose circulates at very low levels, so you have to get rid of the glucose before you can measure the mannose. And this is not routinely done. This needs ad hoc techniques, which we have set up in our lab, but we still have to do it.
And let's say that I have a patient with heart failure that he doesn't want to take SGLT2 inhibitor. But you say that 3-hydroxybutyrate is like a perfect substrate for the heart. Okay? So let's say that that patient, I want to increase ketone bodies in that patient, so he starts fasting. But then you have two competitors for the heart oxidative machinery, ketones and free fatty acid. How would you, reconcile these two substrate competition?
Yeah.
One is bad and one is good.
It's such a good question that there even is an answer for that. And that comes from the fact that the people who have developed the concept of beta-hydroxybutyrate as a preferred substrate, not only for the heart but also for skeletal muscle, they have developed an ester of beta-hydroxybutyrate that is active orally. And they've actually gone public. They've created a company that's currently based in the US, where they sell 25 grams of beta-hydroxybutyrate in a little bottle, a volume of about 50 ml, and this is an over-the-counter product. So it's not yet distributed in Italy, unfortunately, so you have to get it through your American friends, but it's an OTC, so it will go through the ethics committees, hopefully much more easily. And what you do with that, you raise just the ketones, and not much, to about the same level that you would see with an SGLT2, but without touching the free fatty acids. So there are now, if you go on internet, you will find this. It's called HMVD or something, and the company sells this stuff for a very low price, because you get 3 little bottles for $99. Okay? Whereas if you order beta-hydroxybutyrate from Sigma, it will cost you $3,000 for some reason. And it is actually marketed for potentiation of performance, because this group of cardiologists in Oxford, they did the study where they took biopsies, they used this ester before the meal, after the meal, during the meal, blah, blah, blah. Not only did they confirm all the enzymatic kind of pathway that I showed, but this was done in top-notch athletes. And they published in Cell Metabolism, for reasons of time I didn't show the study, that even these top-notch athletes gain in their performance once they... So this is an integrator, apparently with some scientific background, and a cheap one, and safe. It does. There is also available, for example, magnesium beta-hydroxybutyrate, which you can order because it's an OTC thing. I ordered it, and I took it, and I had severe diarrhea because of the magnesium.
Anna,
I don't know. That's a question for them, because I don't want to improve anyone's physical fitness. I just want to use it as a tool to study metabolism.
And a short question, short answer, please. We are.
Thanks, Ale. My few still alive neurons are excited, but I told you this many years ago. A quick question on Team 2, mannose. Is there any relation with the blood glucose in that cohort of CAD positive or negative people? And
Yeah. I did adjust for a few confounders. Again, I did not show the data, but those associations are independent of confounders. Yes. Of course, you can have a lot of confounders. You can put in the cholesterol, you can put in the blood pressure, but then you need larger databases for those.
And is there any intervention so far known able to modify human nose levels?
Don't have the faintest idea, and that would be a good project. When we go back, we'll discuss that.